Equilibrium constant expressions can be used to solve equilibrium problems, to find what your concentration is at equilibrium. So here's an example problem, and in the example problem you have cyclohexane, which is C6H12, isomerizing into methylcyclopentane, C5H9CH3. The only difference between these two is their structural formulas. C6H12 is the chemical formula, but it has a different structure when it isomerizes into this methylcyclopentane. If you notice, you can count up the C's. There's still 6 C's and there's still 12 hydrogen. It's just they're arranged differently. So this happens spontaneously, and the K value has been determined to be 0.12. So you can use the K value and the equilibrium expression to find the equilibrium concentrations for both substances. And that's what I'm going to do. And when I solve this problem, I'm going to use a tool called an ICE chart. An ICE chart stands for initial, change, and equilibrium. So you can keep track of the initial concentrations of the reactants and products, how much they change by, so you can determine what their concentrations will be at equilibrium. Now, in order for me to get the initial concentration of the reactant, I have to use the information that I'm provided. Right here is my molar quantity of the cyclohexane, and this is the volume of the flask. So the first thing I need to do is change that into a concentration. So I'm going to solve for the concentration of cyclohexane and take my molar quantity, which is 0.045 moles, and divide it by the volume of the flask, 2.8 liters. When I do that, I get 0.0161, rounding for significant figures. So this is my initial concentration of the reactant, and I'm going to put it here in my ICE chart, 0.0161. Now, the concentration of reactant I've calculated, but the product over here, this product there's not any initially, so I can put a 0 there. There's not any of it. You don't start out with any of it. And now we need to figure out how much it changes by. So you don't know that value. You have no idea how much it changes by. You're going to determine that. So we do know that, that this reactant is going to decrease by a certain amount. And we're going to let that amount be X. So I'm going to say minus X is what it decreases by. So at equilibrium, my total concentration for the reactant is going to be what I started out with minus what I have lost. So I'm going to say 0.0161 minus X. Alright, now however much this changes by, this goes down by a factor of X. If you look in the chemical equation, that's an understood 1 here and an understood 1 on the other side. So if I lose 1 mole, I'm going to gain 1 mole of the other. If I lose X moles, I'm going to gain X moles of the other. So over here I'm going to put plus X. And when I add these two together, I'm just going to get, I'll put it in the other color. At equilibrium, I'm just going to have X amount of it, which is the same amount that was lost from the reactant. So how do I solve for X? What am I going to do? I'm going to write my equilibrium expression, and I'm going to plug my values in and solve. So you learned how to write an expression, that is the products on the top, the concentration of C5H9CH3 divided by the concentration of the reactant, which is C6H12. Now here I didn't have any exponents, so it's an understood exponent of 1 on both the top and the bottom. And I'm told that at equilibrium, that is going to be equal to 0.12. Now, I can come over here and I can plug in these equilibrium concentrations right up into this formula. And that's what I'm going to do. So on the top, I'm going to have X. Let me start over here. And on the bottom, I'm going to have this one, which is 0.0161 minus X. And all of that's going to be equal to 0.12. Now I'm going to put this value over 1 and I'm going to cross multiply so that I get X is equal to 0.12 times 0.0161 minus X. Alright, and from that I can solve algebraically. I can solve for X algebraically, and I'm going to copy this and I'm going to paste it onto my next slide so I can do that. Put it up here. So now I'm going to distribute this right here. Got to remember your algebra. So 0.0161 times 0.12, that's going to give me X is equal to 0.00193 minus 0.12x. So now all I'll have to do is add 0.12x to both sides. And on the left side, that gives me 1.12x is equal to, cancels out over here. So if you want to keep track of that, you can just line through it. 0.00193 on the right. And so now to solve for x, I'm going to divide both sides by 1.12. And I get x equal to 0.00172. Now, remember if you're just keeping track of that, that went away. This right here, since this is x, this is the amount that was lost from the reactant. It is also the amount of product you are producing. So in my answer, if I want to know the equilibrium concentrations, the equilibrium concentration of C5H9CH3 is going to be equal to 0.00172 molar. And the equilibrium concentration of the other one, we just have to subtract. So I'm going to say equilibrium concentration of C6H12 is equal to 0.0161 minus 0.00172. And that gives me a concentration of 0.0144 molar. And those are my answers. That one. Whoops. And this one. And I believe we've answered our question. Yes, we have.